Now, to measure magnetic field strength or magnetic flux density, we will use an instrument called a Hall probe lah. Specifically, we're going to talk about calibrated Hall probe. So let's talk about Hall probe first, and then how to calibrate a Hall probe. But the Hall probe, how it works is using a Hall effect. So let's look at what is a Hall effect. Now, if you look at this example here, where the magnetic field, can you see, is into the plane of paper, because it's 3D, so it's into the plane of paper. Electrons are traveling from left to right, so this negative Q electrons, so speed is to the right. So the conventional current will be to the left. So if you use the Fleming's left hand rule, you notice that the force is downwards. So what it means is the first electron that travels through this conductor, this is a conductor, because of the magnetic field, it will experience a magnetic force downwards. So the first electron will be pushed down. So when the first electron gets pushed down, it has no problem because there's no other electrons here, so it stays there. But what it means is it makes this side a bit more negatively charged and the top is positively charged down. The second electron, again because of the magnetic field, will cause the force to be downwards. So you get pushed down due to the magnetic force, but because there was already an electron here, so this will cause a little bit of electrostatic repulsion. But as long as the magnetic force is greater than the electrostatic repulsion, the second electron can still be pushed down. And what will happen is the bottom will be even more negative. So the third electron that is supposed to be pushed down due to the magnetic force will now encounter an even bigger repulsion due to the electric force lah. So as more and more electrons get pushed down, while the magnetic force remains the same, the electric force will keep increasing. So they will reach a point when both the magnetic force and the electric force will now be the same. So when that happens, the subsequent electrons will just move straight through undeflected. So when these subsequent electrons pass straight through undeflected, that means there will be no more accumulation of electrons here. So it means the bottom will accumulate the maximum number of electrons, which makes it negative. The top will be maximum number of positive charges, so to speak. So what will happen is you have a maximum PD across the two. So if I connect a voltmeter between the top and the bottom, I will get a voltage, and this voltage is called the Hall voltage. So this Hall voltage is the basis for how a Hall probe works, because in the Hall probe they will also put in a semiconductor instead of a conductor. I explain to you shortly why. When they put the semiconductor here, what will happen is they will allow a current to flow through a semiconductor, and the electrons will accumulate on one side of a semiconductor, and they'll measure the Hall voltage, which is the voltage across the two ends of the semiconductor. And from the Hall voltage, they can tell you how strong the field is, because a simple formula, because later on we're going to do a more complicated one. So FB will be your BQV, and your FE will be your EQ. And the E, which is the field strength, will be the Hall voltage, which is the voltage between these two, divided by the distance. Remember the electric field strength of a charged parallel plate. So it follows the same formula. So this will be VH over D and Q. So the Q can be cancelled, and you will notice that the Hall voltage is directly proportional to the flux density. So the stronger the field, the larger the Hall voltage across the two ends here. So this is the basis of a Hall probe. So how does your Hall probe look like? How do they make use of this? Now they use a semiconductor. The reason why they use a semiconductor is there's this term that is actually covered in the AS new syllabus. They call it number density, which is the number of electrons per unit volume. So semiconductors have a smaller value of number density, so which makes the Hall voltage bigger. Okay, we'll get to derive it later. So the smaller the number density, which is in a semiconductor, the bigger the Hall effect, the bigger the Hall voltage. Okay. Now, your semiconductor, you need to pass a current through it. So you see this cell here? It passes a current through your semiconductor. And the rheostat here is just to vary the current if you need to. Okay. Now, when the current passes through your Hall probe, and your Hall probe is placed in a magnetic field to measure flux density, then the electrons will accumulate on either side, and then you can measure the Hall voltage. Like in this case, if you use a Fleming's left hand rule, you can take the field this way, which is let's say we take 3D to the right. current is into the plane of paper, so the force is downwards. So that means electrons accumulate here, so this is negative, and then this will be positive. Alright, so when you draw, you only draw this lah. Why do you need to draw? Because in your paper 5, in your design question, if the question involves flux density, especially the measurement, you will need to draw a Hall probe. So you draw a voltmeter connected to this. Now what is this? Inside here is your cell and your rheostat, which you don't have to show the details there. And finally, this semiconductor is attached to a pen holder. So your semiconductor is just on this side. Alright, so that's how you label a Hall probe. So how you use a Hall probe is you need to place this Hall probe, which is this semiconductor, perpendicular to the field in order to get maximum force. Now why must it be perpendicular? Remember, because the FB equals to FE, right? So for maximum FB, the current has to be 90 degrees to the field. That's why you have to place this Hall probe perpendicular to the field. So this current perpendicular to the field. But how do I know it's perpendicular? So you need to tell them, so you need to tell them when you use a Hall probe, you need to place it perpendicular to the field. Then you got to tell them how you know it's perpendicular, because the semiconductor slice is just a small piece. So it's not like a very huge thing that you can put a set square. Furthermore, you can't see a magnetic field, so how are you going to know which is 90 degrees? So the technique is to rotate this Hall probe through an angle of 180 degrees. So you rotate it. After rotating, you will notice that the value of the Hall voltage will fluctuate. You get the maximum. The maximum means it is 90 degrees. So you will say, rotate the Hall probe through an angle of 90 degrees to get the maximum reading. So that's what you will say lah. So then the third thing is, how do you calibrate your Hall probe? Because your Hall probe gives you Hall voltage, which is in volts. But you want to measure flux density, which is a unit Tesla. So the simplest way, if in the design question, you want to get one more mark for your additional details or a good design feature, you just have to mention to calibrate the Hall probe using magnetic fields of known strength. That's it. That means you place this in magnetic fields of known strength, you see what is the voltage. Then you place it different fields, you see what's the voltage, then you can plot a graph to calibrate it. But if you want to know the technicality, we look at the next slide. To calibrate the Hall probe, you need to generate fields of known strength, right? So one way of generating magnetic fields of known strength is using Helmholtz coils. This is called Helmholtz coils. Now Helmholtz coils is a pair of flat circular coils connected together, and the magnetic field between the two coils here is uniform if the separation is equal to the radius. When these two are the same, you get uniform field, and the formula is this. But you don't have to memorize this lah. But what you'll notice is the N, which is number of turns in each coil, R is this distance here, which is the radius or the distance, which is the same, and the B will be the magnetic field strength. So let's say you want 1 Tesla, so you substitute 1 here. Then you find out what is the current you must supply here using an ammeter. So then we will know inside is 1 Tesla. We put in the Hall probe right in the middle, so you can put the semiconductor right in the middle here. Rotate it through 180 degrees to get maximum reading. So let's say your voltage you will get as 0.2 volts. So 1 Tesla get 0.2 volts. You double the current, you double the flux density because it's directly proportional current. Then you put in the Hall probe, let's say you get 0.4 volts. Then you triple the current from original, you get 3 Tesla. You put in the Hall probe, get a new voltage. So then you can plot a graph of Hall voltage versus flux density. So that is how you calibrate. Because in future, you can take your Hall probe, put in any magnetic field, read the Hall voltage, and you can find out the flux density. So that's what you can say lah.